So welcome back to today's lecture on parallel graph algorithms. I'm happy to introduce Aiden Bullish, who's a Louis Alvarez postdoc at LBL. He got his PhD with John Gilbert at UC Santa Barbara, and he has released some widely used parallel graph code and is going to give a general overview of that field. But before we get started, let me ask for an announcement about homework one.
Sorry we've taken so long to get you some results and feedback about homework one. I'm going to put up performance curves that we measured by the end of class today on the homework one webpage, and feel free to take a look at those and make sure you think your performance is represented accurately. And if not, get in touch with me. Thanks.
Thank you. Thanks, Jim, for the introduction. Today I'll be speaking about parallel graph algorithms, and I owe some of these slides to Kamesh Maduri, who gave this lecture last year, who is now at Pennsylvania State University. John Gilbert, as Jim said, my advisor from UC Santa Barbara, and Dan Delling, who is at Microsoft Research. So what's a graph, simply? A graph is a set of edges, as typical with the PowerPoints. Okay. Is a set of edges and a set of vertices, essentially. And edges really connect the vertices. This is just to remind you of some of the shorthands I'm going to use during the class. And I use N to denote the number of vertices and M to denote the number of edges. The capital D will be the diameter of the graph, which is really the maximum number of hops in between any pairs of vertices. And the graphs can be as general as you want. It can be unweighted and weighted. And if we mean unweighted, it's really all the weights on the edges are 1. So, and they can have attributes, so they can be, what does this edge encode as in terms of relationship? Is it some sort of connection based on this guy has something else connection? Or practically, it can be as general as you want. But today, we'll be mostly speaking about non-semantic graphs. And the edges can be directed or undirected. And finally, a path is a sequence of edges that are connected to each other. And the length of a path is going to be the sum of all the weights along all these edges along that. So this is going to be the lecture outline today. I'm going to be giving an overview of some of the applications, not all of them, and some important ideas about how to design parallel algorithms. Then I'm going to go into case studies, but it's not going to be just randomly picked 5 case studies. They actually have some nice pattern. It's going to start with graph traversals, which is usually the building block of many more complex graph algorithms. And then you'll see that shortest paths are essentially a generalization of graph traversal that we'll be speaking of, because breadth first search that I'll be speaking in graph traversals essentially solves the shortest breadth problem in unweighted graphs. And then we're going to move on to ranking, which the fundamental algorithm I'll be speaking in terms of ranking vertices in a graph is going to be Betweenness Centrality, which uses breadth first search as a subroutine. And then we're going to show 2 extra to illustrate some of the interesting design techniques that are used in parallel graph algorithms. So applications, really, for a layman, the number 1 application is routing. Whenever you go and type on Google Map, how do I get from one place to the other, it's a point-to-point shortest path query. And there was even an article in Science about that, how to speed this up from 15 seconds to essentially 10 microseconds. And there's a lot to be gained in this field. The internet and World Wide Web, as some of you know, are actually different things, is a graph. And you can represent all the web pages as nodes and all the links as edges. And web search becomes a graph traversal. The ranking and link analysis becomes like PageRank, hits like algorithms. There are different graph problems, and so on. And whenever your packages are routed in the network, it's actually using some sort of Bellman-Ford routing algorithm in the network. Scientific computing, that's probably dear to some people in the audience, as essentially whenever you type A\X for an X sparse matrix, in the background what happens is the system tries to calculate an ordering on how to proceed the elimination of the equations, and that ordering tries to minimize the fill-in that occurs during LU factorization of a sparse matrix. And this is guided by a graph. And you can actually see what happens. This picture corresponds to that graph. Every time an equation, and actually a variable is eliminated from the equation, you get an edge that makes all its neighbors chordal, essentially. Chordal means for every group of vertices, every angle, which will everything that's bigger than a triangle will have a chord. If you think about this red edge, if it didn't exist there, there would be a polygon of 5 vertices which didn't have a connecting vertex. So essentially it comes from graph theory. And a lot of iterative methods as well. This was for direct methods. Iterative methods have support theory from spanning trees and some other graph embedding. And incomplete factorizations are also guided. People use graph matching to get the heavy entries on the diagonal so that the factorization is more stable and so on. So there's a lot of graph algorithms here, and there's a reference for those who are interested. Large-scale data analysis in many scientific applications, such as astrophysics, bioinformatics, and even really ecology and so on, scientists conveniently model their data as graphs. And here you can think that the items in the galaxy as nodes and their particular interactions as edges. In bioinformatics, you can think about your proteins as vertices and their sequence similarity, functional similarity, whatever, as your edges, and so on. In these kind of applications, the challenge is quite different than the previous one because these are really massive data sets of terabytes and petabytes of data, as opposed to some of the little ones that I gave here is actually much more complicated, but in a more manageable scale, at least. If everything is relative, of course. And I thought there was a slide about social informatics. You can find out whom to target if you're going to do some sort of advertising. So you want to figure out what person connects societies, different clusters together, so that if I target my ad to this person, it's going to spread as fast as possible. Really, how do I make my video go viral as easy as possible is find those people, influential people. And I'm going to be speaking more about those things in the Betweenness Centrality and ranking part. Intelligence and surveillance, similar story actually to the previous one. Suppose you know the underlying network in a different country. Your intelligence agency has collected information about a group of people in the town, and you know how they interacted, how they met, who called whom at what time, and who texted whom. But you don't know the ringleader. You can't go and arrest 1,000 people at a time. So you want to figure out whom to target first. And again, it becomes centrality questions, and then some really anomalous activities that happen in the network. So you can think of it as a pattern that existed in how people log into supercomputers. And every time a particular pattern arises, that kind of leads to an attack on that system, because it's not really a person, it's a bot. It's a bot that automatically does that. So subgraph isomorphism tries to detect those kind of anomalies before it happens. And a lot of those. Okay, really. But the research in parallel graph algorithms essentially is a very complicated a table like this. You have a lot of applications, some of which I've talked. You have a lot of methods to solve them. Really, it's not really supposed to be read, but different graph methods. And then there's algorithms that you use to build those methods. And there's a lot of architectures you want to target. So every time you want to target an application area, you kind of find the problems you want to solve and the algorithms that are needed to solve those problems, and finally, which architectures you want to implement those things. So it's kind of a complicated story. And this is the reason. It's a graph, yeah. It's a directed graph. It's actually a cyclic graph. But today, there's a piece of this research that I'm not going to be speaking about, which is graph libraries. So you never want to do this thing from scratch for every different architecture. So you want to use graph libraries that implement most of these algorithms, hopefully, on most of these architectures. So when you need it, you actually just do composition. but I'm not going to be speaking about most that. Again, so how do you choose which algorithm to use is essentially, it depends on your input data size. So you want to find paths, clusters, partitions on that input data, but which kernel to use and what algorithm you pick to implement that kernel is depends on the graph sparsity. For algorithms that are for dense graphs are quite different than algorithms for sparse graphs. One of them that's optimal for dense graphs. The diameter plays a big role, and vertex distribution plays a big role, whether it's directed, undirected, and so on. So there's a whole lot of zoo out there, which is it's impossible to cover in a lecture, but I'll try to touch a few pieces of it. So designing a graph algorithm. Most of the clever algorithms in graph analysis, the parallel algorithms, came in the so-called PRAM model. PRAM models, have you seen PRAM model? Yes. Essentially, it has some issues with ignoring too much of the communication costs and assuming infinite number of processors. But it led to very clever algorithms, some of which can be mapped nicely to current architecture. Some of them are totally impractical. But there's a lot of insight to be gained. And 80s had a surge of extremely clever graph algorithms based on this PRAM model. And as I said, some of those really it becomes the algorithms become independent of the network topology when you're dealing with the PRAM model. So you don't need to think about whether you have a hypercube or how much will be time will be wasted when I call an all-to-all primitive on P processors. But the disadvantages actually come from the same reasons, because they lose touch with some of the reality, to say the least. And the techniques mostly used to design PRAM graph algorithms are some of the techniques you've seen in the Tricks with Trees lecture, like how to do prefix sums, how to do alerters, pointer jumping, really data parallel primitives, mostly, I should say. And some of these are nicely implemented in current architectures, such as GPUs. But when you go to more loosely coupled architectures, like distributed memories and so on, it doesn't work that well. Instead, I'm going to be, in some of the algorithms, I'm going to be using a slightly related model called work-span model. This is really related to PRAM because, in a way, it also ignores communication costs, but it tells you what is possible in the best scenario with a given algorithm. So work TP is the execution time on P processes, and assume that this graph, this directed acyclic graph, is models the different pieces of the execution of this code. So every node here is some sort of task that needs to be completed, and every edge is a dependency. So you can't start one vertex before all of its dependencies have been finished. So T1 is considered work. So how much time would it take for a single processor to finish executing every single task in this graph? And so you have to go over all of them, of course. T infinity is span. You're going to see from the animation. It's really, if I had infinite number of processors, how fast can I execute this directed acyclic graph? And your parallelism is actually the ratio of work to span. There is not more speed up that you can gain from this code. This becomes sometimes important because it tells you what is the best speed up you can achieve for. And there is, of course, pretty simple laws that the time on P processes will never be super linear, which is not true, actually, in practice. Sometimes things can start fitting your cache suddenly. But as an idealized model, that's probably true. And the span law simply says this time to run on P processes is never going to be less than running on infinite number of processors. OK, how do you represent graphs? Essentially, whenever you deal with an algorithm, data structures become one of the fundamental question. because a right data structure can make a very complicated algorithm pretty trivial. So for the static case, if you have a dense graph, you just use adjacency matrix. For any ij entry in that matrix will be representing the edge that goes from the ith node to the jth node. For sparse graphs, you either use your textbook adjacency lists, but I'm going to speak about something else, a little bit compressed sparse matrices, which you have seen in previous lectures. They become more cache-efficient alternatives to adjacency lists, and they got pretty good traction in the recent decade or so. For the dynamic case, it's much more complicated, and the right algorithm really depends on the update rate, so how fast my graph is.
Could you distinguish static and dynamic?
Yeah, so a static graph is your input is fixed, and you're asked to do some sort of calculation, some run on this graph, and your input will not change either during the algorithm or pretty much for your interest, it's static. For dynamic graphs, is essentially you want to maintain some sort of property. You want to maintain communities or clusters of the graph, but constantly, whoop, that always happens these days. Constantly you get updates for this graph. So really, how much you want to pay for the penalty of provisioning those updates really depends on how frequent they happen. If they're really happening in batches and infrequently, maybe you don't want to optimize so much because a dynamic data structure is usually cache inefficient. There are going to be a lot of pointers to facilitate constant time updates on that data structure. And of course, it's really the query to update ratio is the number one important thing. PowerPoint has this thing that it records my presentation and it changes in predetermined moments. I couldn't figure out how to see. It comes really good. So graph representations really this is a dummy graph that I use, just 4 nodes. It even has self loops, and all these italic numbers are the weights on the edges. And your textbook representation adjacency lists will have a vector of size 4, which has pointers to adjacencies, the outgoing edges of all of these vertices. So take 4, there is an outgoing edge to 2, weighted 14, and there's an outgoing edge to 4 himself, weighted 7, something like that. But let's say how compressed sparse rows kind of data structure actually looks like, exactly this. So you have an, let's assume that you put these things together, and instead of pointers, you put integer values that serve as pointers to the next array. So 1 points to the 1th location, 3 points to the 3rd location, 4 points to the 4th location in the other array. So instead of real pointers, you just put integers. And then you stick those adjacencies together. So all of these values together in 2 arrays, in parallel arrays. One of them represents the adjacencies, the other one represents the weights. Now you see the analogy that essentially this is compressed sparse rows. So indices become row pointers, adjacencies become column IDs, and weights become numerical values. And why would you do this as opposed to adjacency list is essentially every time you jump into a pointer, you're making a cache miss. Since we've said that these graphs are static graphs, it's much easier to actually just stream through these entries without doing any kind of cache misses. This was all what's going on in a single processor. But when you need to distribute this graph on clusters of processors, let's say distributed memory, you have multiple options. If your graph is small enough, you can replicate that in every single processor. In general, that's not the case. So you will, what is the most natural representation, actually, without looking at the slide? Let's say you have a graph like this, and I ask you to, and I tell you that there are only 2 processors. Now, how would you distribute it? The most natural way of thinking about it. Yeah, divide what half in half? Okay. The easiest way to manage this thing is divide vertices into half essentially. So the first two vertices would go to the first processor, the second two vertices will go to the second processor. And that's what we call one-dimensional partitioning, because when you look at the adjacency matrix of that graph, you're actually chopping it in a one-dimensional fashion. You're chopping it along the rows. And it's also called a vertex partitioning. You just give the first N over P vertices to the first processors, the second N over P vertices to the second processor, and all of the outgoing edges go with them there. There's an alternative, the edge, but you don't want to randomly distribute edges, because then you don't know who owns what edge. It becomes totally a nightmare, and the bookkeeping becomes fairly unscalable if you just treat every edge as a separate entity that can go anywhere. Instead, you do something like a more structured way of distributing the edges. So assume that you have 9 processors. In that sense, yeah, please.
Previous slide, there was still a couple of bullets.
Yeah, there will be a lot of bullets, unfortunately. But this is mostly to serve as a reference. So I'm not going to be speaking every single bullet. Thanks, though. So when you have, let's say, 9 processors, you would assume them as if they're distributed, they are in a logical processor grid of something close to square root of P by square root of P. And in this particular example, it's 3 by 3. This is the sparse adjacency matrix that represents this graph. And every different color shows a different processor. So this piece goes to one processor, this piece goes to the other processor. And the advantage of this kind of distribution over one-dimensional distribution, which will become clear later, is that whenever you're speaking, you will be speaking only with your row neighbors, these 3 guys, or column neighbors, these 3 guys in most of the algorithms. And you can understand the scalability benefits. If everybody in this room tried to come to a consensus on a subject, it will take a lot of time. Instead, what we do is we divide people in groups of 4. Probably there will be 4 groups, actually, it looks like. And then those are going to come to consensus independently and tell us what they've done. It's much more scalable. To get high performance in graph algorithms, as some of those I already said, you want array-based representations, typically, to minimize the cache misses, CSR representation for static graphs. You want to minimize the number of synchronizations in your graph, essentially to get much more, as much parallelism or concurrency as possible. And that's the span that I've talked about. And for distributed memory, the distribution that minimizes inter-processor communication is crucial. So it's the typical question, where is the data question. And memory access patterns are fairly important in graph algorithms, both spatial locality and temporal locality, if it exists. Some graph algorithms will never have any temporal locality, in that sense that an item that's fetched from the memory will never be used again. So there's no point in optimizing for that. But for some, there will be some temporal locality. And lastly, work efficiency is something that's to be targeted as much as possible, which means really, am I doing more work than a serial best algorithm would do? Sometimes this is not possible, but as much as it is achievable, we try to get there. So let's go into some of our case studies. Graph traversals. Breadth-first search, I will be speaking of mostly, but why not depth-first search? So there's 2 ways, essentially, of traversing a graph. Either you can go depth first or breadth first, and I'll first show what depth first search does. This is a recursive implementation of depth first search. Please don't implement this ever, because it's going to blow your stack. But it's much easier to show it on the slide. It's just 5-6 lines. So whenever we start traversing the graph from 0, let's say, we call depth first search 0, and it marks it as visited and calls depth first search on one of its neighbors, and it recursively will go on. So it's really like this. It's going to explore second and mark it as 1 because it's the first one after the root. And then recursively, it's going to call its one of its neighbors, and then it's going to unfold. And what's going to happen after this? Hopefully, it didn't record, and it's not going to suddenly show up. So we came to 6. We explored its neighbor. It doesn't have any neighbors. It backtraces. It goes explores 9, actually the opposite. Then what's going to be the next to explore? 8, because it has another neighbor. The recursion will backtrace and go again to 8, and then 7 and 5. OK, so what's the problem with this algorithm in terms of parallelism? Now, how do you parallelize depth first search? You essentially can't parallelize depth first search. There has been a lot of attempts, but none of them actually managed to get a span that's less than the number of vertices. So no matter how many processes you have, the span of depth first search is essentially a number of vertices, which is pretty puny. And there's actually a paper, a famous paper that shows why this is the case. Depth first search is inherently sequential. And for those interested, you can. Some people didn't believe in that paper because it's not a proof, of course. But still, there is no algorithm that span is less than ON, as far as I know. So that we deal with an alternative way, depth first search. And I should say, depth first search was a great algorithm for some cases. You will see that the ordering here is a very peculiar ordering. The numbers I put is pre-order, so you number before you call your adjacency, your neighbors. You can do a post order or some other order as well. But this ordering allows some very clever algorithms to run in linear time, in serial. But it doesn't work in parallel, unfortunately. So breadth first search essentially traverses the graph in a different way. It marks all the vertices that are one hop away from the source as 1. And the vertices that are 2 hop away from the source is 2, but it explores them at that time. All the vertices that are 1 hop away from the source will be explored at the same time, typically. Not necessarily. So that's where the parallelism will come from. So in the output, really, the first hop neighbors are going to be marked 1, the second hop neighbors will be marked 2, and so on. So the numbering is quite different. The memory requirements of breadth first search is linear. So M is a number of edges. Again, N is the vertices. We will have a stack of visited vertices, and we will need an array that represents the distance from the source vertex.
Actually, isn't it a queue? Or do you mean stack?
Well, no, I think it's a stack. It doesn't really matter because you'll never, yeah, it doesn't matter because once you put them on the stack, all the 5, 7, 2, it doesn't matter which order you put them out from this queue. It's still going to be a correct breadth first search. It matters a lot in depth first search. It needs to be a stack there. But here, it actually, requirements are not that strict. The way to do breadth first search in parallel depends on your graph. If you have a low diameter graph, meaning that the distance from the source vertex to the ends is pretty short, in that sense, you will do a level-synchronous approach, where you're going to start from the source, explore all the vertices that are 1 away from each other, synchronize all the processors, and in parallel go to the next step. So every one of these ellipses is a parallel step, essentially. But when you have high diameter graphs, where this is unfeasible, imagine that your graph has a diameter 1,000, and you don't want to take 1,000 steps, because this is a linear time algorithm. In many cases, this is going to run in less than half a second in practical inputs. You can't do 1,000 synchronizations on your supercomputer for that. So you will do an approach that's due to Ullman and Yannakakis that chooses a group of a set of different starting vertices and runs path-limited searches. What that means is it runs a breadth first search independently and tries to reach to square root of n neighborhood first, and then collapses them as super vertices, runs an all-pair shortest paths between those super vertices. It's a much more complicated algorithm than the level-synchronous one. And I actually didn't see a parallel implementation in the current architectures. So if somebody is interested, it might be a great project. But we'll be talking about more simple things, the level-synchronous strategy. And first, we're going to look at how this affects the locality. Now, don't think about yet parallelism, because the parallelism is going to come a little after that. What happens when I have already explored the first frontier? So these are in my stack, and I'm trying to create the next frontier. Really, let me actually come out all of them together, or maybe too much. You will be accessing all of these vertices at some point during the iteration. For every vertex, you will visit once, hopefully, if your algorithm is not incorrect. So in a total number of accesses you'll do to index to the adjacency arrays is ON. But for every one of those vertices, you will scan its outgoing edges. Throughout the execution of the algorithm, you will do it once for every vertex, scan its adjacency. So there's going to be an OM access. This is not, the first one will be perhaps a random access. The second one will be something that we call a stanza access, because you will do a random jump somewhere in your sparse matrix, and you will make a streaming access for all the adjacencies of that vertex. So that's what we call stanza. And then later, you're going to check whether a vertex is visited or not. Unfortunately, you will check a vertex multiple times. You will check a vertex as many times as it has incoming edges. So that's why, for example, this is the access of checking whether you have visited the neighbors of the current frontier. You'll see that 0 happens multiple times because many of these guys are still trying to access 0, although 0 has already been visited before. So you will make those accesses to the visitor array. The performance, though, is really going to close the track how big this frontier is currently. And here's as a practical plot. This shows on the red curve the time that's spent on that phase of the breadth-first search iteration. And the black curve is the number of frontiers, the number of vertices on the frontier array. They closely track each other in different inputs. If you want to zoom in.
So the point was that nobody's more than 15 nodes apart from any other person in that network. That's what.
That's actually. So we're talking about the level-synchronous approach. And we said that level-synchronous parallel approach is very suitable for graphs with low diameters. And that's why you'll see this are representative inputs. It actually stops exploring the graph around like 10 phases. And you will have all the vertices covered by then, maybe 15. There will be a little bit left there. But you will never make 1,000 phases of breadth-first search to actually cover all the vertices.
So this is the proof of 6 degrees of separation, right? Because that's where the
both of these are social networks. Very good point. So this is Flickr and YouTube kind of friend interactions or contact. Flickr calls them contacts, I think. So we talked about this locality, but we didn't do anything about it so far because there isn't much you can do. But I will touch one possibility to do something about it. So that's your sparse matrix that represents your graph. And what if you order its vertices? So I mean, that's really permute the matrix, symmetric permutation, and you get it in this form. This still represents the same graph, but it will hopefully have better data access patterns. And why is this the case? And I won't really talk about these. I will talk about this option. So think about this guy, 90, which one? Yeah, 44. So 44 will be accessed by 31, and then by 74. If they don't come next to each other in my queue, by the time I check 44 again, it's going to be. It might possibly be depicted from my. It might fall out of my cache, and I will need to bring it back in. So the idea is, if I kind of order this graph in a nice way, that all these people that I will need to access, 0, 84, 93, it's going to be nicely packed together. And I won't need to fetch them back to my cache and see them fall out of my cache, and so on. So that's kind of the idea that exists in sparse matrix computations as well. It's typically an NP-hard problem, but we kind of do some sort of orderings that help Cattell-McKee, reverse Cattell-McKee. Well, the objective is some sort of cache blocking. So this is what I've talked about in the previous slide. Instead of really going through the adjacencies of every vertex on the frontier one by one, try to pack them together so that you will actually have blocks of adjacencies that fit into your cache. And in general, if you have high-degree vertices, that's going to be pretty hard to do. So you will do them separately, and the low-degree vertices, you will try to cache block. And of course, there is no theoretical proof that that will work. But in practice, you can get speed-ups up to a factor of 3 and so on, which is fairly important in practical terms. So the red line is without ordering, and the black line is if you cache block it. And the higher is better because this is a performance metric. Just like flops, this is edges traversed per second. Millions of edges traversed per second. Performance. And this nicely ties to a recent benchmark called Graph 500. So just like Top 500, there is now a benchmark that ranks supercomputers based on their ability on how fast they can do data-intensive computing. And breadth-first search was chosen as the representative benchmark for that. Evaluation criteria is really the one that I just talked about, highest performance rate. How many edges you can traverse per second. The input is given. Yeah, it scales up in the sense that it's a synthetic graph generator that tries to resemble the social networks in a way that it has power degree-like distribution in the vertices. It has low diameter, so small word graph. And the NERSC-Hopper system is currently ranked number 2 on the current list, which can do over 100 billion edges traversed per second. And I claim these are going to improve because still the algorithms are improving. The machine will stay the same, but the algorithms are going to improve. So how do you do a breadth-first search on a supercomputer? We just showed how to do breadth-first search locally, and then perhaps on a single node with multi-threading. How do you do breadth-first search on a supercomputer? For that to be well understood, I'm going to show a way to do breadth-first search using just linear algebra operations. So this is a graph, and this is the transpose of the adjacency matrix that represents this graph. For every edge, there is a dot. A dot is just a Boolean entry. I drove it for transpose because I'm going to show the breadth-first search as a column operation. So in that sense, the outgoing edges of 1 are in the first column, as opposed to being in the first row. So to do a breadth-first search starting from 1, I multiply my matrix, my Boolean matrix, with an integer vector whose only entry is 1 in the first location. And I replace my scalar operations of multiply and add with select, and if there are multiple things to sum together, summation becomes minimum. So after the first iteration, what I'm going to get is 2 1 entries in the second and the fourth location. That's exactly what I wanted, because I want to set parents of 2 and 4 to be 1. So I output them, I prune them, I prune the previously visited ones, and I go to the next iteration. I remark them as 2 and 4 because they are in the second and the fourth location. I do it again. Since in this case there are 2 entries that needs to be summed together, because 7 can be reached by both 2 and 4, although I didn't mark, so because it doesn't succeed, we choose 2 just because we chose minimum as the summation. You can choose maximum or arbitrary. It's not going to change breadth-first search correctness. And by doing this operation as many times until the right-hand side vector becomes empty after pruning, you're going to be done, and you're going to you will have your parents array successfully constructed. Very nice. So what does this tell me? This tells me that all I need to worry about to parallelize breadth-first search on low-diameter graphs is to parallelize sparse matrix times sparse vector. The data access patterns are going to stay the same. So let's see how what happens in the vertex distribution, one-dimensional distribution case. As I said, the first n over p vertices goes to the first processor. The second n over p vertices goes to the second processor. Now they're represented as columns because this is the transpose. If it was the actual adjacency, it would be the rows. And a different color represents a different processor. The algorithm is essentially a local discovery because this guy is just going to scale its columns, a local discovery. But it can potentially find entries in the next frontier that belong to various different processors. So there will be an all-to-all exchange to let them know that those vertices are discovered. And people will, the recipients of these messages will update their distances and parents array locally. So the problem here is just the all-to-all communication. And to change that is to use two-dimensional distribution, the checkerboard kind of distribution that I've showed before. In this case, it's not that obvious who owns what in the graph vert, but it's fairly obvious how to chop this matrix off, right? You just put a simple checkerboard distribution. If you really want to know what's going on the graph, it's a little more complicated. And I should say that the blue and the red processes collectively own the first 4 vertices and its outgoing edges. And how those outgoing edges are partitioned are depending on where they're going. So if they're going to the first 3 processors, 1, 2, 3, then they're red, owned by the red processor. If they're going to the other ones, they're owned by the blue processor. But it would take me days to figure this out if I was looking at this picture. Instead, it's fairly obvious on the matrix one. Now, what has changed in this algorithm is now since every edge doesn't have its starting point, there's an extra phase you need to do to gather the vertices, and then the rest is the same. Except all the communication is taking place in either the either the processor column or the processor row. So there is never an all-to-all communication among everybody in the room. There's groups of all-to-all communications, which makes it a little more scalable. And that's the practical result. On the left side, you see the performance rate that includes everything. Gigateps is billions of edges traversed per second. On the right, you see communication time. This time, the lower is better. So in both of the cases, we see that the two-dimensional hybrid algorithm, where hybrid means inside a single chip, you do multi-threading, and in between chips, you're doing MPI communication. And you already know that hybrid ones are going to be more scalable than flat MPI codes on Hopper, and that's kind of another proof to show that. But the real story here is two-dimensional algorithms do significantly less communication and achieve better performance on these kind of graph inputs. I'm not going to claim anything about any other graph. That's all about breadth-first search. Any questions? Yes.
So have people tried to express the Ullmann-Yannakakis algorithm in terms of linear algebra?
I don't know it yet. Yeah, according to best of my knowledge, no.
Okay, future work.
Yeah, well, it's not hard actually, because all it does is path-limited breadth-first searches. We already know how to do breadth-first search in linear algebra. And then it's an all-pair shortest path between super vertices. We know how to do it in linear algebra. So I would say it would be a good exercise.
If you go back 2 slides.
Sure.
I didn't understand how you split up the matrix. Maybe I missed it.
Normally, you will just split it up so that the first n over square root of p by everyone would typically own n over square root of p. But since this is only 7 vertices, it doesn't exactly fit. So this is a 2x2 processor grid. You have 4 processors. And everybody would ideally get 3.5 by 3.5 block. Since it doesn't work like that, we kind of take the ceiling and floor. OK? All right, so let's go to shortest path, which is really what we have seen as breadth-first search can be used to find shortest paths on unweighted graphs, because every time the weights will be 1 in that case, and breadth-first search just suffices. For graphs that are weighted, we have more complicated algorithms. So the famous algorithms for single-source shortest paths are Bellman-Ford or Dijkstra. And the Bellman-Ford one is a label correcting algorithm. And this word, if you hear it again, all it means is once the algorithm passes through its vertices, it can still come back and correct these distances. As opposed to Dijkstra is a greedy algorithm. Once it's done with those vertices, it's finished. It will never come back to those vertices. It's a more clever algorithm, but Dijkstra only works on graphs with non-negative edge weights as is. You can pre-process the graph maybe to get rid of this requirement, but you will need to do one Bellman-Ford to pre-process that graph, which works any graph. It's m times n, so it's not anything close to linear. Dijkstra, on the other hand, is this. This is the Dijkstra's coast, actually. No parallel algorithm, even in the PRAM model, actually achieves Dijkstra's coast. There's added factors in there. And essentially, there is a great experimental analysis. You can look at this paper. And it's also mostly concerned about the delta stepping algorithm, which we'll be focusing on. So this algorithm is a very nice algorithm. It's a label correcting algorithm. It can come back to the same vertices again. And it runs in time NMDL for random edge weights. And I'll tell what that means and why this is the case. And at D, we know that it's the diameter, and L is the maximum distance from source to any node. So the shortest path weight, maximum of the shortest path weights from the source. And this nicely degenerates into those famous algorithms. If you choose delta too small, it degenerates into a bad implementation of Dijkstra without heaps. And if you choose delta too big, then it degenerates into some sort of Bellman-Ford, and it does too many correction steps.
Does it assume non-negative edge?
I think it does assume. Because, yeah, because there is a stepping delta, and it's not clear what it means to step negatively. So here's how the algorithm works. Let's assume that we choose delta to be 0.1. First, from our starting vertex 0, we're going to inspect all the edges and mark them as light or hence as less than delta. Its weight is less than delta. If it's heavy, it means its weight is more than delta. So what delta means, we're going to construct buckets. Each of them contains distances of delta sizes. So the first bucket is going to contain all the vertices that are within 0.1 of the source vertex. The second bucket will contain all the vertices that are at least as far 0.1 far away, but as not far away as 0.2, and so on. Why we are dealing with heavy edges later is that there is no way the first vertex is going to go to the first bucket anyway, because the first bucket is defined as far as 0.1. Well, okay, one can come back. No, it's not going to come to that bucket due to that edge. It might come back from another source. So we look at the light edges. In this case, there is only one. And we create requests. It's a technical term from the pseudocode. It's not that important. The more important thing is when we go to another vertex, we're still in the first bucket. So that's kind of the interesting part. We started executing this while loop while the current bucket is non-empty. And we can execute this while loop multiple times. So processing a single bucket, unfortunately, is not a single parallel step. It can be multiple steps. And we will only finish when all the distances are above the first delta size. So we will execute the first iteration, the second iteration, and at that point, we will go to the second bucket because our distances, our bucket will be empty. And from the first bucket includes 0, 2, 3, and they have outgoing edges to 6, 4, and 5. Now is the time to deal with the heavy edge pairs. And so one of the interesting things of this algorithm is they will all go to different buckets because one of them is really much more farther away. 6 is going to go to the 6th bucket. 4 is going to go to the first bucket because its distance is going to be 0.16. 5 is going to go to another bucket as well, potentially. The algorithm is a little complicated to teach in a class, but the point here is the complexity of the algorithm can be changed depending on the graph by choosing a different delta.
Is the parallelism over a single bucket or over multiple buckets?
Unfortunately, it's neither one of them. So the parallelism is within one execution of the bucket. So this inspection is going to be in parallel. And this relaxation will be in parallel too. But it performs pretty good. In the worst case, you can construct inputs that this has no parallelism at all, just as bad as the depth-first search. But the good news is, as opposed to depth-first search, practical implementations of this algorithm actually scales on many graph instances, except high-diameter graphs. So in low-diameter graphs, the number of phases of this algorithm is actually pretty short. This is scale-free graphs. This is some random Ardashirani graphs, which I haven't talked about much. But this is scale-free graphs like social networks. And the number of phases that are needed is just 100, which means like your span is only 100, essentially. But for high-diameter graphs, you can see that this is quite a lot. You won't get too fast. And we had the same problem in level-synchronous breadth-first search. High-diameter graphs were not suitable. But as opposed to the breadth-first search case, I'll actually speak about an algorithm that works with high-diameter graphs in this case. And it's also, the algorithm is also affected by the average shortest path weight because L was the maximum distance. And actually, they kind of closely track each other. For high-diameter graphs, average shortest path weight, even after normalization, is higher than these low-diameter graphs. So now I'm going to talk about an algorithm that actually works on a different kind of input. It's a very recent algorithm called PHAST, Hardware Accelerated Shortest Path Trace. It's a bad name for a smart algorithm, I should say, because it has nothing to do with hardware. The algorithm is very smart. The way you do this algorithm is you first pre-process your vertices, and you kind of assign a random number. It's not that random. There is an intuition behind that. It's called a highway dimension. You assign highway dimension to your vertices. And if you're dealing with road networks, this is more obvious. You will assign highways higher levels and sideways lower levels. So think of it that way. And then you do a pre-processing which adds shortcuts to preserve distances, which I won't go into detail. But for those who remember some kind of sparse matrix factorization, it's essentially the same thing that happens when you decompose A into L and U factors. You will get fill. That they are called shortcuts in this algorithm. For road networks, the fill is really small because road networks are almost planar. They have very good separators. Don't try this algorithm in scale-free networks. It won't work. But this is great for road networks with high diameter and great separators. Now, OK, we assigned levels. Like it says, for example, it was 150 different levels were assigned in the kind of road networks that Dan and Andrew Goldberg had tried. And then let's say you want to start, you want to find out the shortest, single source shortest path tree from the source vertex 4. So you make an upsweep, bottom-up sweep of the data. And you will only visit these vertices that are higher than you are and directly reachable to you. You will not go down back to 6 or anything else. So you will get to the highest highway as soon as possible. Yeah.
That was my question. The intuition is you go get on the highway, spend most of your time there, and then get off in the little streets again. Okay.
And that's why we add these shortcut edges, because if we were exploring everyone, we didn't need any shortcut edges. We add the shortcuts so that getting to highway if there is a short distance to get to the highway by going first to 3 and coming back to the 7, it's included in the shortcut as well. That's why the pre-processing takes care of that problem. So this step is, in a way, only goes up to more important vertices only. Now, once you touch the highway, which in this case the 7, you go directly down to all the other vertices in a linear sweep. So here's, yeah, of course. The crux of this algorithm here is that you will go level by level. So you will not reach to 2 before you reach to 6. Since this is the case, you don't need to keep a heap. You know that you are only visiting vertices in different levels at every stage. You don't need to keep what is the smallest one. Instead, you just need to do a linear sweep and try to respect the triangle inequality and relax them accordingly. And if you have noticed that once you reach 7, how you go down from this step is really input independent. For every input, whether you start the shortest path from 4, 5, 3, 2, in the second step when you're doing the down sweep, you're always making the same execution. The values will be different, but data access patterns are going to stay the same.
You mentioned the triangle inequality, which is certainly true for roads, but not every graph. Is that an assumption here?
Yeah, that's kind of... oh, no, that's not an assumption. That's not an assumption. Okay, sorry, no. It's just the relaxation rule, I should have said. Thank you. So the second phase becomes a linear sweep, and it becomes data independent. The values it will set depends on, of course, how much it took to get to 7 and so on. But what kind of vertices you're going to visit is independent of the short source vertex. What this allows is that you can reorder this whole computation, the the top-down sweep, and make sure that the sweep is just over a contiguous memory segment as opposed to making jumps. So that's the crux of the algorithm. And once you do that, you can parallelize it with all sorts of single instructions, multiple data parallel manner, either on GPUs or using SSE instructions. And you'll get pretty good speedups. And you see that this is a very well-optimized Dijkstra code. One of the co-authors, Andrew Goldberg, spent his lifetime optimizing shortest path algorithms. So it is good code. And in that sense, PHAST can beat this thing to a factor of, I can't calculate this, like 50 or something like that. Yeah, on pretty much all the different inputs, and whether the input, these weights are estimated arrival times on between cities or towns, or the actual physical distance. It doesn't matter. And if you implement this thing on a GPU, then you're getting even faster, of course, because GPU has more bandwidth, and we have converted our top-down sweep as just a stream operation. And the more bandwidth we have, the faster the top-down phase will go. And it does actually go really fast. You can't implement Dijkstra efficiently on GPUs as far as I know. Again, the last disclaimer is that this algorithm is specifically designed for special kind of networks. It doesn't perform that good on general graphs, especially that doesn't have good separators. The reason is the fill-in on the pre-processing is linear, so it doesn't hurt the performance. If you had other kinds of graph, that would be quite different. Now I have a very, okay, it looks very bad on my computer, but here it looks good. So we're going to go to ranking, and I'm going to be slightly quicker here because most of these slides I have here actually talk about breadth first search, and you'll see why. So Betweenness centrality is, centrality in general tries to assess the importance of vertices in a graph. Or it can be edges if you take the dual graph. And you can answer questions like, who's the most influential person in this research community? Who's the most influential person in this terrorist cell, and so on. Betweenness in particular is based on shortest paths. And this whole formula captures the betweenness centrality score of a vertex. And here, the sigma st is the number of shortest paths between S and T. Sigma st v is the number of shortest paths that pass through V. That's all. So it really answers this question, among all the shortest paths in this graph, between all pairs of vertices, what percentage of them are passing through me? Yeah, how good of a connector I am. If you have dense graphs, of course, you can just run all pair shortest paths, get the output, and use it to estimate Betweenness Centrality scores. But that's not going to be very efficient in terms of space and time if you have a sparse graph. So the Brandeis algorithm works great in a sparse graph, and it runs in linear time, MN time and linear space on unweighted graphs. And you will just add an extra log n factor for the weighted cases, because the breadth first search is going to become Dijkstra's implementation. The crux of the algorithm is a recursion that says dependency of the source on any vertex, which is really the sum of all the shortest paths from S to any source that passes through V is the dependency, can be represented by this nice recursion, which says that I will look all my outgoing edges, and the dependency of S on me is the ratio of the number of shortest paths to my neighbors divided by, the number of shortest paths to me divided by the number of shortest paths to my neighbors multiplied with 1 plus. And the proof is in the paper for those interested, but it's actually not that complicated proof. So it's a backwards thing. If you think about it, in order to calculate the dependency of V, I should have calculated the dependency of all of its outgoing edges. So all of its outgoing neighbors, all these W's here. So that's what we're going to do. The high-level algorithm of this, the high-level idea of this algorithm is you make a breadth first search. So you first calculate all the shortest path lengths, because this is unweighted. Breadth first search will solve that. And then you will use this recursion to accumulate the dependencies by a backward sweep from the endpoints of the breadth first search. So 2 breadth first searches and some extra bookkeeping. That's all it's going to do. And there are great shared memory algorithms that are work efficient, later improved with removing some of the dependencies. If you're interested, feel free to take a look at them. But the illustration is really a breadth first search. And I will not go into details because we've already seen how breadth first search works in level-synchronous step, and how complicated it can get in terms of locality accesses. And the accumulation step is really going back from these endpoints backwards and using this recursion formula to update dependencies. So it's a breadth first search with a different kind of semi-ring, if you catch the linear algebra connection. How do you implement this thing on distributed memory? I'm just going to mention one possibility, which is to use sparse matrix multiplication over a different semi-ring. We've already seen in breadth first search that how to replace multiply with select and how to replace addition with minimum. Now, the forward step will exactly be that. The backward step, the tolling of the dependencies, will going to be a different floating point operation. It's going to be divide all of the parents by its number and update. But what do we gain by implementing this operation by sparse matrix to sparse matrix? Well, you see in the right-hand side matrix, this is for every starting vertex, there is one non-zero. So breadth first searches from 3 different starting vertices at the same time. So this nice algorithm will encapsulate 3 levels of parallelism. Since we will be automatically parallelizing over columns of B when we parallelize just this operation, we would be parallelizing multiple breadth first search in parallel. And since we're going to be parallelizing over columns of A transpose and rows of B, this translates into parallelism over frontier vertices. If you have 100 entries in the frontier, that's the parallelism. And finally, since we're parallelizing also over rows of A transpose, this is where we get parallelism over high degree vertices by its many outgoing edges. And you can see how this works in later sections of this paper. There's a performance result. Betweenness centrality is not the only way to rank a graph, a set of vertices in the graph. Perhaps more famous algorithm is PageRank, but they rely on very different metrics. They're not finding the same thing. Betweenness centrality finds vertices that connect communities that are influential, and that's a metric. PageRank works in different definition, which just says, if important people point to me, then I should be important too. But then, of course, where does this definition end? Because where does it start? Who do you know is important in the first place? Is essentially you solve the power method. You calculate the stationary distribution of the system. It's essentially the stationary distribution of a macro process, and it's just an eigenvector calculation, eigenvalue eigenvector calculation. The trouble with that is the matrix is pretty big. This is probably old numbers. The matrix should be a couple orders magnitude bigger than that by now, if you can crawl all of it. But the point is, PageRank all boils down into sparse matrix vector multiplication. At least it used to. It has since changed and incorporated a lot of other things, but the heart of the algorithm is just sparse matrix vector multiplication, and a lot of other tricks to make it go fast. OK, any questions? I'll go into a very interesting algorithm that's not based on graph traversal. So far, everything we have seen uses some sort of graph traversal. Shortest paths, betweenness centrality, breadth first search, needs to visit every single vertex in a structured way. Here, the algorithm will see Luby's algorithm, and indeed your classmate, Michael Luby, it finds the maximal independent sets. So that's a very important algorithm, the primitive in many different scientific computing applications. So maximal independent set is find me a set of a set is maximal independent if no two vertices in the set are neighbors of each other. Essentially, so 5 and 4 are independent vertices. So you want to find a set that's maximal. That doesn't mean maximum. You can find a bigger set than this. Maximal just means that I can't add any more vertices to this set. So I'm stuck to a local minima. That's what it says. The maximum one is NP hard, so that's why we're not dealing with it.
Just to remind the audience, we talked about these maximal independent sets when we did graph partitioning.
OK. Did you talk about the algorithm too?
No,
Okay.
Just said, talked about the simple sequential greedy algorithm.
Yeah. Exactly. So you know the simple sequential greedy algorithm now. It looks like this. Thanks. But now you know it's important, actually. You start with an empty vertex, and then you traverse all the vertices, and if none of its the next vertex has a neighbor to the ones that are inside the set already, you add that to the independent set, and eventually you will just add 1, 5, 6. Of course, I didn't talk in many important details here. How do you check if something is in the set? You need a really fast set inclusion, data structure, whatever. But in the end, you can get it to run in close to linear time in terms of work. But the span is also close to linear time if you implement it sequentially like this. Instead, I'll talk about a really interesting and very common algorithm paradigm in graph algorithms, randomization. So this is a randomized algorithm. You can de-randomize it once you get the idea. It gets just more complicated, but it's much easier to understand when it's randomized. So what happens is you have two sets. First, S is your output. C is the current set of vertices that I didn't process. Let's call it this way. And you randomly label, you label every entry in C with a random number, like this. And then every one of them independently looks at its neighborhood and checks if he has the minimum number. So who's going to be found is 5 is going to find itself as having the minimum numbers, and 1 will find himself to be the minimum among its neighbors. So they will go to S, and all of both 1 and 5 and all of its neighbors will be removed from C because they can't be on the independent set anymore. Now we run this again, and we will get other random numbers for 6 and 8, and one of them will go into the independent set. That's all. And you can prove with very high probability that this will finish in log n rounds. And you're doing more work. This is not work efficient. You're doing log n more work. But since your span is just log n, you have ON parallelism. This is a highly parallel algorithm. And it works very well in practice. Pretty cool.
If you were actually going to implement this, how do you ensure that you don't generate the same random number?
You actually want to generate the same random number, right? I mean, no. You mean like for different vertices or different processors?
Yeah. So if you accidentally generate the same number for 2 different vertices, that would break the algorithm, right?
You generate random numbers to different vertices. Well, is this a common case or it just suddenly happens?
It just suddenly happens, like it's worst case.
Well, it doesn't matter, right? I mean, you can always break those things as undecided and go to the next round. You know, you can assume that they're undecided, or you can toss it again. If it was the case, like the case that always happens, then we will do something about it.
There is a literature on parallel random number generation which avoids that, so it can be fixed.
Okay. So the last case study will be very short because I'll just show that an important primitive cannot be implemented in its most efficient way in serial. So strongly connected components is really to find these blocks. Find the largest possible component where you can go from every vertex to every other vertex. This only makes sense on directed graphs, because in undirected graphs, a strongly connected component means just connected component. Here's, you see, if this was an undirected graph, forget about the directions and make all the edges as undirected. This whole graph is a single connected component. But strongly connected component means you can actually go from one place to every other vertex in that strongly connected component. So that's kind of a different definition. And this graph has 3 strongly connected components. And these are decomposed like this in the matrix. It has applications on sparse matrix algebra, but really the best algorithm to do that is a very clever algorithm due to Bob Tarjan. It uses depth-first search as its fundamental building block. And we already know that depth-first search is inherently sequential for all unfortunate purposes. The better algorithm to do this is a divide and conquer breadth-first search. You do breadth-first searches from 2, I don't have a slide for this, actually. You do breadth-first searches from a vertex, and you try to reach as many places as possible. And then for all the places that you can't reach, you recursively call them later. So it's kind of a worst-case performance of algorithm is pretty bad, like it's ON, puny. But again, just like delta stepping, it works very well in practice.
What's the worst case work? The worst case span is order n. So the worst case work is like n squared?
No, it's not n squared. I think it's n log n. M log n, because this is already m. Yeah. So let me finish with some of the things that we already said and try to come up to a conclusion of this lecture is really whether it's parallel or not, if you're going to get high performance graph analytics run, you need to care about one thing is locality. So this is a typical picture of how the performance is affected by increasing the problem size. The same kind of input, just double the size, same characteristics of the input. Your performance rate drops significantly as you fall out of different levels of cache. You probably have seen this same story in linear algebra and all sorts of other applications. That's not that typical for graph algorithms. But just saying that there is no way to avoid this problem. Just because your algorithm is doing a lot of cache misses, you should not go and say that, oh, it's already doing too many cache misses. Why do I worry about cache locality? Parallelism, there's a lot of text in this slide, but the more important things is really the topology assumptions in some of the algorithms don't match the real data sets. So first look at your data set and figure out what was the best algorithm that's possible to solve your given problem. And locality is important in any graph code. For shared memory, you want to minimize the locks and barriers. For distributed memory, you want to care about communication.
Question, the loggerheads means that, if you want to get more parallelism, it requires more communication. Is that what you're saying?
In general, yeah.
Yeah, okay.
So designing parallel algorithms, this is a kind of a space. We have different algorithms. Some of them run in quadratic time, some of them run in linear time, some of them run in n log n time. We have different problem sizes. And really, our accesses can be as good as stream-like, like linear over the memories, or as bad as random access, like every single access is totally random. So really, you want to try to improve locality by pushing this down. You want to compress the data because we've seen how much effect the data size has in terms of the performance rate. And you will try to discover faster and faster methods in terms of minimizing the work. So that's really the whole research zoo on this area. Best algorithm depends on the input. Communication costs are very crucial for distributed memory. For in-node, locality is very crucial in terms of cache locality. Graph traversal, specifically breadth-first search, is a very useful building block for more complex algorithms. And really, in many cases, best parallel algorithm is quite different than the best serial algorithm. So don't always try to lift your favorite algorithm to parallelism. Sometimes it might work, but if it doesn't, you might need a more radical, different thinking. Yeah, thank you.
Thank you, speaker. So I know there are some people doing their class projects on this kind of stuff, so we can't have all lectures in the beginning of the semester, so we pack them in whenever we can. So, so are there any questions? Okay, so Aydin is certainly around a lot, available at LBL, so if you have any questions, he's around.
You're welcome.